Hello and welcome. I'm Shadow of Shadow Gaming, bringing you episode 20 of Programming with Shadow. So this one we're gonna move in and do you can see here over and we'll go. We're gonna build a linked list. So this is a data structure, and we're gonna apply a few more of our techniques and build another data structure up. That last time I might try to do namespacing. We'll look at that in the future, but it's not today. We'll do sort of a review and little furthering our data structure knowledge instead. So I'm going to start with paint here first. So just a little diagram. So the linked list has a node. I'm using these as nodes. Node A, node B, C, and D. So you have a node, and then that node tells you where the next item is. This is called a singly linked list. You cannot have doubly linked list too. And then you would have an arrow that goes the other way too, so you can go backwards and forwards. We're just going to implement forwards for now. So linked lists have some interesting properties, but they are generally not the correct structure to use. There's occasional uses, but a lot of times they're not correct. Here's one thing that they're nice with though. When we add something to an array, if it's at the end, we can just add to it unless it has to be expanded. With a linked list, it's nicer to insert in the middle, though. You don't have to move everything else down. You just change where this is pointing. Let's say we wanted to add E here in the middle. Here, box, E here. So then all we got to do is, paint's not a good one here. Erase this. Over here and get me an arrow again. That's a terrible arrow. But here, let's undo that. Not that big. There. Very quick. So there's how you insert though. We'd point B to the new one and point the new one to whatever B's previous was, and we're good. That's where linked lists shine, is you can do stuff like that. Or that's two operations. We don't have to move C and D. They can stay wherever they are. So an array, you can think of them as everything in memory. It's all contiguous. It's all together. Linked list doesn't have to be together. You just have to have a pointer to the next one. So that's what we're going to be doing today. Is we're going to be implementing this. We might look at it for performance. I'm not sure. Let's go ahead and get started. So let's do a new file. Let's call it node.cs. Do public class node. I'm using a generic here just so we can have whatever value we want. Let's see. Node, get nullable next. So I'm making it nullable because we don't have to have a next node if we don't want to. Need to be a node of T. There we go. So that should be as a node. So one thing to note here is we have a value, we have the next, and that here value would be whatever's inside, and next would be where it's pointing to, and all we really need for it. Come over here and make call it singly linked list .cs. I was about to forget the .cs. All right, so let's do public class singly linked list of key. So I'm doing this generic. Let's see, we want what do we want? We want let's start with the data. So what you need to know for a linked list is you need to know the starting point, and you can also know the ending point and keep those if you need it. So I'm just going to do the starting point. I think. So if you have both, you can go backwards and forwards through the list, and that's called a doubly linked list. Let's do them both. So I designed this back last week, so I don't remember why I needed both. So let's see if we can get to that point. So first off, let's have a count. So we'll keep track of how many nodes are added as well. This is technically not required. We could do count the other way. The other way is to start here and go 1, 2, 3, 4, 5 and count each time. The nicer thing you can do is just whenever you add a node, just increment a count, and that way you keep track of it a little better. So let's do that. Track of count, that's a private int. There's a count. Let's do a is empty. Count equals 0. That can just be useful. You can use it to check if the list is empty before you do anything else. You can also just get it from the count, but whichever one works. All right, let's do a method. This is where most of the work for the list is. So there's two ways you can do this. You can add it to the beginning or you can add it to the end. The other one's going to be an insert where you insert it into the list. So we'll start with add. Let's add to the front. So the front's easy. So public void add first t value. So we'll do node of t new node equals new value. New node dot next equals head. So what that's doing is it's taking whatever's here and it says, okay, add here, and your next value is the previous, so it adds it to the front of the list. So now we can do head equals new node. And there we go. We've added it. Now we can also do this if tail is null. Tail equals head. So that just updates to tail if we need it. I can't remember if I really wanted that or not, so we'll come back to that and increment the count. So the increment the count's just because we're storing the count inside. Like I said, we could do it linearly if we wanted, but this will be a constant access, so a little nicer. We'll take this, the object initialization. We can just initialize it as we create it. All right, and that's just telling me you can. Oh yeah, let's look at that. Compound assignment. I don't know if we've actually mentioned that before, but I actually don't mind that. So that says if tail's null, it gets head. That's all that means. I don't know if we've actually talked about that though, but that's just special syntax. It's the exact same thing as that if check. If it's null, sign it. If not, don't. So we can do that and there. And I did not do that in my example, so we are now off the rails, but that's fine. So if we add it from the other end, it's easy as well. So it's very similar. Public void at last t value. We'll do this same thing here, except last x is null. I guess it would be null by default, so don't need that. The reason next is null is to add it to the end of the list. There's nothing, like if I add one here, I point this one to it, but then there's nothing there. So if tail is not null, tail.next equals new node. So the tail should already be null, so the next should just be settable like this. There's an else condition though. We need to handle the head. So there we go. So I haven't seen that before. So there I'm saying the head and the tail. So that here the tail is not null, so here the tail is null, and if the tail's null, that means there's nothing added. We have added up here. But nothing's, so the tail, if the tail's null, the head's null, so then we just set all three of them together. And you could do that separately if you want. Like this is the same as if you do actually you have to do it the other way, but should end up the same thing. Have to do it like that instead, but we'll just do it like that, and then we'll do count plus count. And there we go. That should be add last, I think. So let's go check. So let's do a trying to think how would be a good way to let's do here let's go ahead and implement IEnumerable of t. I think I want enumerable. Is it? No, this is it. So this one, get a numerator. This one let's implement as node t of current equals head. So start at the beginning and then while current is not null, square brackets, braces, yield, return current dot value. Next. Current equals current dot next, and I think that's all we need. So yeah, let's go check what happens here. So let's do we'll just do int so let's do a add first. Let's copy that. Let's do 2, 3. So that should get us to order 3, 2, 1. So let's actually undo that and put them in the correct order. Then let's do for each list. The console dot right line L. So what this does. So let's do .NET Run. So what I want this to do is print 1, 2, 3. So let's see if it does. Well, it has to run. Well, while it's going, there we go. 1, 2, 3. Let's do a add last. Set a 4. Linked list. Add first. Put something in front of everything. Then do repeat this. Now we should have the order 5, 1 or 9, 1, 2, 3. Or not. Oh yeah, that's right. Yeah, I didn't put a space. Yeah, I was like, wait a minute, what's wrong there? Just forgot my space. So there we go. So yeah, so that works. Let's continue. So let's do a remove. So removes are easy. So the remove will get the value for us. You could just have it get rid of it if you wanted. You could also have instead of a remove, you could have a find, be able to find the value you're looking for if you wanted. Let's begin. So if it is null, throw new invalid operation exception. Linked list is empty. So we can't do that. However, if it's not null, then grab the value, grab the node, I guess. And here we removed it by just getting the next one. And I think we're good. So then we want to adjust the count. Now if it is null, and tail also needs to be null. Return value. I think that's all we want to do. It's nice and simple. So all we do is we grab the head, we set the head to the next value, and we increment the count, and if the head is null, we're done. So remove last is very similar. Do public t remove last. So this will just grab the tail. Linked list is empty. Then if head dot next is null, there's only one, so then we do set everything to null, set the count to 0, and return the value. Else, so wait a minute, do we even need to do that? Wait a minute, we have tail. Might could actually just use tail here and just do it. We'll continue. That's if there's one value, otherwise current equals head. So here's what I was thinking to do. While so loop through while it's not null. Once it is null, then we know we're at the last value. That's not right. Wait a minute. This should be the last one. Yeah. I've messed up my logic here. This should be value. I'm glad I didn't try just copying what I have, whatever prototype, because it's going to be wrong. I think. This is going to be wrong too, isn't it? Yeah, wait a minute. So the problem here is with it singly looped, you don't know from here, you don't know what C was, so you have to figure out what C was to find D. So let me think. Current is current, all current is next. Now I was right, so I do want to do that. Yeah, that's interesting. What I'm wanting is the second to last node. So in my example, I want C. So this should be next. We just checked if it wasn't null, so should be good. I'm gonna have to think on that to make sure, but let's try it and see. Let's see what happens. So now let's do now we have 9 at the front. We'll do for var int removed equals let's do removed. Now let's remove the last value. Let's print it first. So here we should remove the 9. Then we'll do this. Now we'll remove the 4. Let's see if it dies. It might die here. We should print 1, 2, 3 though if we get it correct. 1, 2, 3. All right. I did have it right. So there's this remove last. So here, this is the condition. There is only one node in the list. So we could use count there to check that condition as well. Here, get the second to last item in the list. There we go. So let's do let's do a contains method. Let's do node of t current equals head for head. All right, so let's do a compare. And we shouldn't need this. We shouldn't need. We don't need to. Do we? I'm wondering if my node needs to have a compare. We'll come back to this. So let's just do while current is not null. If current dot value that may not be a good comparison. Even work. Yeah, there we go. We'll add that. Now we can do whatever the default comparison for the type is. So that's something we would have to remember and have to adjust if we decided to use object in the as a node. We'd have to remember that we did something like this and I have to adjust. However, this is just going to use the comparer and use whatever the default is for the value. And give it the next and return false otherwise. There's just a contains. I guess if we wanted to do a get, it's the exact same thing, except we return the value we're trying to get here if we wanted to. Could do that, I guess. Public void clear. Here's another common collection one. Head equals tail equals null. Count equals 0. So there we go. There's just a clear. So we don't actually get rid of anything if you notice. C#'s a garbage collected language. That means when something's no longer used and it's all null, it should eventually get garbage collected for us. So there, this is a linked list. So let's do console.writeLine. Linked list that contains 2. If it's 2, contains 2, does not contain 2. Let's copy that. Do none. Here we'll do that. Here let's do WriteLine clearing list. Now we can do linked list dot clear. Now we can print it out and we should get a lot of nothing. Do after. There we go. Let's do that. So now we should see it contains 2, does not contain 9, prints out the list, clears it, and then prints out a bunch of nothing. There you go. There we go. There's just a very quick implementation of a linked list. So one thing we can do more let's think. Let's do a insert. So the insert here I did was insert after B. I think that's the one. So let's do that. Let's do insert after T existing value, T new value. All right. Let's do node of T current equals head. Let's get our quality comparer. All right, so now while current is not null, this is going to look very similar. Oh, I can't hit the braces today. At least my mouse isn't moving. So if comparer equals current dot value existing value new, that's what it is. It's node of T new node equals new value. Add the next equals current dot next equals so if current is tail equals the new node, count plus plus, return true, else current equals current next. And then here, we get all the way down here, it's a, let's look back at that. So if they match, then we create a new node, we set the new node's next, whatever the current node is. So B, we set the next a minute, is that right? Yeah. So next, so E gets whatever B's next was, which was C. So then current next points to E at this point. That if it's the same, we need to set the tail, and then we're done. There we go. So that is a insert, I believe. We'll test it over here. Let's insert here before we clear the list. Let's insert after the 2. Insert after 2, and let's insert 7. So let's see what happens. There we go. Inserted the 7 after the 2. There we go. There's just an insert. So that was a good quick implementation, or some features. We might could add something else if we wanted, but I think this is going to do us for now. So let's look at the complexity for stuff. Let's start here with the latest method. We mentioned complexity. It's done as big O of something. So that stands for, in the worst case, it could take this, how long it could take. So insert after. So in the worst case possible, or in the worst case possible, it's easy. It's big O of n, so it's linear time. So in the worst case possible, let's say we have this. Let's say we want to insert let's insert f after we find node z. It would be an A, not A, B, not B, E, not E, C, C, D, not D. If we didn't find a Z, we return false. False. We fall out of the loop, return false. So we had to loop through the entire list. You could see if you had a really big list, that might take a while. So that's the insert. So actually adding was pretty easy. Finding where to add it, not so much. Nothing you have to do though to move everything, so we don't have to worry about moving the value. We just have to find it. So not hardly as bad, but there's the worst case. Let's look at clear. Clear is very easy. That looks constant, and in fact it is. Big O of 1. Big O of 1, so constant time. It'll always take the same number of operations. Contains is the same thing. It'll look through the entire list in the worst case. So big O of n. Here, remove last. So last is interesting. So we might have to move right up to the end of the list, so it could possibly be big O of n. And in fact, it has to be because it's big O worst case. So in the best case, heads null, we're done, or there's only one and we're done. Both of those are constant. Always the same amount of checks. If there's more than one node, so say if there is one or fewer nodes, big O of 1. But in reality, the method itself would be big O of n. Here's the interesting one. So constant, 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 and constant. So inserting at the first, it's constant time. And if you don't care about order, that'd be pretty easy to do. If you care about order, you would have to use that's not right, constant time. If you cared about order, you would have to do some kind of find the value where you want to put it, then put it in. So you're looking at linear time again. Not really any benefit. Get a numerator. And you have to look through the entire thing. Get the last value at last. You go with 1. We only loop through at the very end. We don't even look through. Big O of 1. Ignore that. Is empty. Because of how we did it, it is O of 1. Count is O of 1 as well. The others data, they don't have the complexity here. So that's what we got from that, is the what we got from that is that a lot of the complexities there were 1, and in fact, if we do we go look at our cheat sheet here, I think I had linked list, singly linked list. There we go. So access is 1, search is 1, insert and deletion are 1 if you're doing it from the first or last. It's this one we should be looking at. Space complexity is linear as well, so each time we add a new node, we have to add the node. So that matches what we just calculated here as well. So constant. There are some linear methods to remove last. So in general, if you have something, a list you want to do a lot of additions to, you can add it to the front and remove from the front. Then you'd be pretty okay. I think another data structure called a queue can be used to do something like this pretty easily. So the idea there is you just keep adding and removing from the first or last element, and it can be fairly nice to do that with. In general, though, most of the time in C Sharp, list of T is going to give you a little better performance than the linked list. So there's some overhead. You have to have a node. You have to have data stored separately, and there's some overhead. One other thing. There's a linked list here. There we see it says it's system collection generic linked list of T represents a doubly linked list. So C Sharp already has one of these built in, and if we look here, method. There's add first, add before, add after, add before, add after a node, add before a node. So a lot of that stuff we just implemented here. See if there's a remove. There's a count. Find. We didn't do find. You could add a find if you wanted. Where's remove? There's remove. Remove first. Remove last. So remove removes the specific value. I would say it removes the first one you find. I'm not sure. Yeah. There's some other methods, but these are just extensions. But yeah, so C Sharp has one built in. And in general, if you were actually using a linked list, that's what you would want to do instead of implementing it. But by implementing it, you have knowledge of sort of what concerns there are and how it works. That can be useful too. Like I said, in general, it's more of a learn about though, because conceptually, it's really easy to think through this and do this. Usefulness, I've never wanted to use a linked list. I have used them. I have used them a couple times, but it always feels like you're not going the right way, even when you use them, and not just be what I'm working in, but that's how it always felt to me. That sign in. I don't want to think. But that's linked lists. So in the future, we might take this knowledge here and look at implementing other data structures. So back here on the cheat sheet, arrays and arrays we've already looked at. This we've now looked at. Doubly linked list is interesting, but only because it's the same thing. Except you can go forwards and backwards. So you would add a node, you would add maybe a previous, something like that, and then you can go back and forth through the list, and you can do some optimizations based on that. Next, two data structures though are these: queue and a stack, and we may look into them in the near future. Namespaces are coming as well, so there's at least 3 topics we might in the future. May look at actually implementing using something as well. We'll see about that. So let's recap what we've covered today. So today been a little slower day. Been implementing a linked list. So linked list here implements the IEnumerable of T interface. So we're using generics So the data of a linked list, we're doing count here, so we don't have to loop through each time. We have a constant time count. So all that says is we always just know the count, so we can always just retrieve it, and that's all it takes. We don't have to loop through the list and figure out how many values are actually in it. We added a couple methods. Add first. We noticed that add first is really nice on a linked list. On a singly linked list, we always know where the start is, and we just add to it. And add last was almost as nice. Just have to know that make sure you add the head as well. We looked at this. I want to say it's null assignment operator. I'm actually. I was wondering if it would tell me what that actually is called. But what that means is, I think it's null assignment, but it says if tail is null there, that it's equal to head. And you'll occasionally see that, and sometimes it can make stuff actually look pretty clean. Add last, nothing interesting. We see multiple or assigning multiple things in one line. Not really impressive, but something you can do. Here's the implementation for IEnumerator. Must have accidentally pushed the other one down. And there's the get enumerator. So there's the implementation for our interface. Then we did the removes. Not really anything impressive with the first. We just grab the first value, adjust the head, and adjust the tail if needed, and we're done. Remove last is a little bit more work. And notice it's big O of n, which is linear time. So as the list grows, it constantly takes a little more time. And that's because we have to loop through the list if there's more than one. So you have to loop through and find the second to last item, and then you have to adjust for that. The reason that's required is it's a singly linked list, so we can't go back and forth. If it was a doubly linked list, that becomes a little easier because then you know who the previous node was and just adjust like that. Contains exactly the same deal. You have to be able to loop through the entire list in the worst case. Clear is easy. You just set everything to null and you're done, and you let C#'s garbage collection handle the rest. Last one we implemented was insert after, and it's very similar. You have to find the node you're looking for, which could be in the very last position, could be not exist. Then you have to loop through and find it, make the adjustment, and then you're done. So I believe that's going to do it for the day. I think that'll finish this lesson out. I'm going to come here and click this here after we're done. So we'll break there. But next, as mentioned, in the near future, we're looking into namespace and then looking into more data structures. At least stack and queue, maybe a priority queue. We'll see. But that's what you can look forward in the future. So I'm going to call it there. So thanks for watching and have a wonderful day.